Hey guys, welcome to the second part in the series on complex numbers. In the previous video, we solved exercises on basic algebraic operations, adding, subtracting, multiplying and dividing complex numbers. In this video, we will take it a step further and solve exercises on how to take roots of complex numbers, for example, the square root of I. And then we will use this skill to solve quadratic equations that involve complex numbers. The timestamp for each exercise can be found in the comment section below, where you can also ask any questions you have along the way. And with that, let's get into it. We start out by looking at how to take roots of complex numbers. And we will start out with a very basic exercise just to refresh one of the crucial properties of complex numbers. Let's say that we have to take the square root of minus 16. Now, we know that for real numbers, this is not defined because we have a negative number under the square root. However, it is different for complex numbers because we know that for complex numbers, we have the special identity that I squared is equal to minus 1. And from this, it follows that if we take the root on both sides of these two numbers, then we get that I is equal to the square root of minus 1. So evidently, we can take square roots of negative numbers. And to solve this exercise, we first write this minus 16 as minus 1 multiplied by 16. And of course, we know that a square root of a product of two numbers is equal to the product of the square root of each of these two numbers. So the square root of minus 1 multiplied with the square root of 16. Now, we know, of course, that the square root of minus 1 is simply I, the imaginary unit. And we know that the square root of 16 is simply 4. And therefore, the result of this exercise, the result of the square root of minus 16, is simply 4i, a purely imaginary number. So this is how we use complex numbers to deal with square roots of negative numbers. However, what now happens if we have to take the square root of a complex number, for example 3 minus 4i? We see that this is a complex number with a real part and an imaginary part, as defined in our previous video. Unfortunately, taking the square root of such complex numbers is not as easy as taking square roots of negative numbers. However, there is a systematic method which you can use to always get the right result. The first step of this method is to assume that the square root of a complex number will itself be a complex number. And we can write it down like this. So the complex number will be x plus y times I. And of course, just writing this down didn't solve the exercise at all. It just shows that we now have to find two variables, the x and the y. And if we found x and y, then we of course found the square root of 3 minus 4y. So how can we find x and y? Well, the first step is to realize that we have an identity here. And if we take the square on both sides of this identity sign, we can rewrite our exercise in order to find x and y. If we square this side of the identity sign, the square root simply drops. So we get 3 minus 4i. And on the right hand side of the identity sign, we simply square x plus y times I like this. This, of course, can be calculated even further. So we copy the left hand side, 3 minus 4i, and the right hand side we simply write out. So we have x squared plus 2 times x times y times I, and we add to this y squared times I squared. And in this last term, we of course note that I squared is equal to minus 1. It's basically the definition of I. So we can drop this I squared, and we can replace this plus sign with a minus sign. Rewriting this even further, we get that 3 minus 4i is equal to x squared minus y squared plus 2xyi. And why did I rewrite it like this? Because at this point, we can clearly identify the real part and the imaginary part on both sides of this equality sign. We have this 3 and this x squared minus y squared being the real parts, and minus 4i and plus 2xyi being the imaginary parts. And because for equality signs with complex numbers, we always compare the real parts with each other and the imaginary parts with each other. And this gives us effectively two equations. We get an equality sign for the real parts. So we have 3 is equal to x squared plus y squared. And for the imaginary parts, we have minus 4i is equal to 2 times x, y, I. And this is a system of two equations that we now want to solve for x and y. Because again, if we have x and y, we can just fill it in right here and we have the solution to our square root. And let me call these equations 1 and equation 2 just for future reference. And with future, I mean right now, because if we take equation 2, we can find an expression for y. We see that we can simply cancel out this I in both sides of the equality sign, and we get that 2 times xy is equal to minus 4. Or rewriting this as a function of y, we find that y is equal to minus 4 divided by 2x, or written differently, minus 2 divided by x. And this now gives us a relation between y and x, and we can use this relation to fill in our first equation, equation 1. So let's do that right now. This first equation gives us 3 is equal to x squared plus y squared. And of course, we now know y squared simply as being minus 2 over x squared. We simply filled in y, which we found from equation 2. This gives us a direct equation being 3 is equal to x squared plus 4 divided by x squared. And this is simply an equation in x, which we now solve to find a value for x. So how to solve this equation for x? What kind of equation is it actually? Well, if we multiply both sides of this equality sign with x squared, and thereby getting rid of this x squared in the denominator, which we don't really know how to handle, we get the following equation. 3x squared is equal to x to the power of 4 plus 4. And rearranging this equation, we get the following fourth order equation in x. We have x to the power of 4 minus 3x squared plus 4 is equal to 0. And it is now this fourth order equation that we want to solve in order to find a value for x. And if we find a value for x, we can find a value for y. And again, if we find a value for y, we have our square root of our imaginary number. So how do we now solve this fourth order equation? Well, we first note that we only have even powers of x. We have x to the power of 4, x squared, and x to the power of 0, which is simply 1. What we can do in such cases is say that x squared is equal to u. So we just redefine x being the square root of u, or x squared being u. Using this substitution, we rewrite our equation in the following way. So we get u squared minus 3 times u plus 4 is equal to 0. And we see that using this substitution, we now rewritten our fourth order equation, which we don't really know how to solve, as a quadratic equation, which we do know how to solve. A quadratic equation has two solutions, and we can easily solve them by writing them like this. So these two solutions, u plus and u minus, are equal to plus 3 plus minus the square root of 9 minus 4 times a, which is 1, times c, which is this constant term right here, is times 4. And we divide this by 2a, which is simply 2 in this case. And if you're not quite sure how I got these two solutions, then I gladly refer you to my video where we solve several quadratic equations with this method. We can calculate these two solutions simply being plus 3 plus minus 5 divided by 2. Or this gives us two solutions for u. U plus is equal to 4. And u minus is equal to minus 1. And again, remembering that u is equal to x squared, we get several solutions for x squared. So for our first solution, we have x squared, which is equal to u, which is equal to 4. This is our first solution here. And we have our second solution, x squared, which is also equal to u, is equal to minus 1, which is our second solution right here. However, because x is a real number, we see that x squared can never be minus 1, because the square of real numbers are always positive. So we can discard this solution, and we're only left with this solution right here. So now that we have a value for x squared, let us go back and see how we could connect x with y. We saw right here that y is equal to minus 2 divided by x. So now we can, of course, first rewrite this right here so we don't forget it. So y is minus 2 divided by x. And since we now know that x squared is equal to 4, this means, of course, that x itself is equal to plus or minus 2, because plus 2 squared is 4, but also minus 2 squared is 4. This gives us, again, two solutions. Let's say that x is equal to minus 2. Well, this means that y, being equal to minus 2 divided by x, will simply be equal to 1. And the second solution, when x is equal to plus 2, then we know, of course, that y is also equal to 2 divided by x, which is now equal to minus 1. And there we have our two solutions. So we have x is equal to minus 2 and y is equal to 1. And our second solution is x is equal to plus 2 and y is equal to minus 1. And there we have our two solutions for x and y. And let us simply remind ourselves why we did this. We see that the original exercise was finding the square root of 3 minus 4i. And we've written this square root by assumption as being x plus y times I. And at this point we found our x and y and we found two solutions, which means that our square root of our complex number can be, of course, two values. So let's now simply fill these values in. So our original exercise was the square root of 3 minus 4i. And let's now see what this becomes. The first solution of the square root is equal to minus 2 plus I, because we know that x is minus 2 and y is equal to 1. And it has a second solution being 2 minus I, which of course comes from these solutions right here. And this is the definitive answer for the question what the square root is of 3 minus 4i. It's basically two solutions, the complex number minus 2 plus I and the other complex number 2 minus I. And before we go to the exercises on how to use this skill now to solve quadratic equations, let me just say that you can use the same method that we used in this exercise to calculate the square root of I. And if you do so, you will see that it is not as trivial as you would think. Let's now go to the part where we look at how to solve quadratic equations. And here there are two scenarios, so two kinds of exercises, one easier one and one more involved. And let's first start with the more basic one. Let's say that we have z squared plus 2 times z plus 5 is equal to 0. And here we know that z is a complex number. Now you can use the same method of solving quadratic equations with real numbers. The only difference here is that with complex numbers you will not run into the problem of having to take square roots of negative numbers, because for complex numbers this is not a problem at all. Let's see how this goes. So we have, of course, two solutions, z plus minus, which is equal to minus 2, which is minus this coefficient right here, plus minus the square root of this coefficient squared, so 4, minus 4 multiplied with this coefficient, which is 1, multiplied with this coefficient, which is 5. And we divide this by 2 times the coefficient in front of the z squared, which in this case is, of course, 2. We can simply calculate this, so we get minus 2 plus minus the square root of 4 minus 20. And 4 minus 20 is minus 16. And we divide this by 2. And at this point, the difference lies, because if we were working in R, so for real numbers, then we would just stop here and say that this quadratic equation does not have any solutions. However, because we're now working with complex numbers, we know how to take the square root of a negative number. This is even exactly the same exercise that we did at the beginning of this video, the square root of minus 16. This means that we can write this as minus 2 plus minus the square root of minus 1 multiplied with 16 divided by 2. And again, this will be minus 2 plus minus I times 4 divided by 2. Or if we write it even differently, we get minus 1 plus minus 2i. And these are two solutions, a plus and a minus solution, which will make this equation hold. And if we want to be really sure, then we can of course always check our solution by filling in our solution in the original equation. So let's take minus 1 plus 2i as our example. So we first square it, then we add to this 2 times this solution, so 2 times minus 1 plus 2i, and we add 5. And now we want to know if this is indeed equal to 0. And if it's not, then we made a mistake. So let's see how this works using the operations that we saw in the previous video. So this will simply be 1 minus 4 times I plus 4 times I squared. But of course we know that I squared is equal to minus 1. So this plus sign can be rewritten as a minus sign. Then we calculate this term right here, which will become minus 2 plus 4i. And we have this constant term right here plus 5. And now what do we see? We see that this minus 4i and this 4i cancel each other out. And we are left with 1 minus 4 minus 2 plus 5. And if you do your arithmetics, then you see that this is indeed 0. So we didn't make any mistakes. So let us now go to a more involved exercise, which you will also encounter and which you would want to be able to solve. The problem here is the following one. We have z squared minus 1 plus I times z plus 2 times 1 plus I is equal to 0. And the difference now here is that even in the quadratic equation itself, we have complex numbers right here. However, this same method of solving the quadratic equation still remains valid, and therefore we can just start calculating. So we have our two solutions, z plus minus, is equal to minus the coefficient in front of the z, which is in this case plus 1 plus I, plus minus the square root of the same coefficient squared. So this becomes 1 plus I squared. And here I already omitted this minus sign because a minus sign squared simply becomes a plus sign, minus 4 times the coefficient in front of z squared, which is easily 1, multiplied with the constant term, which is 2 times 1 plus I. And we take the square root of this and we divide this whole thing by 2 times the coefficient in front of the z squared, which is in this case simply 2. So at this point we just use our good old method of solving quadratic equations. So nothing different really happened here. So let's see what we get if we calculate this. So we get 1 plus I plus minus the square root of 1 plus I squared. Now 1 plus I squared, we just calculate. So we have 1 plus 2I plus I squared. And we know that I squared is equal to minus 1. So let's already write that here, minus 1, which again is I squared. Then we subtract from this, 4 times 1 times 2 is 8. 8 multiplied by 1 plus I. Take the square root and divide this by 2. We see that this one and this one cancel each other out. And we see that here we have 2i, and here we have minus 8 times I. So this becomes 2i minus 8i, which will be minus 6i. So let's just write that down for clarity. So we get plus minus the square root of 2i minus 8i, which is minus 6i, so minus 6 times I. And what we're left with is this minus 8 times 1. So this simply will be minus 8. So we take the square root of this complex number and we divide by 2. And we see, of course, here that we need to calculate the square root of this complex number. And this is exactly what we learned in the first part of this video, taking the square root of a complex number. And that is why we can now use this skill to solve this quadratic equation. So let's use the skills that we learned to solve this square root. So we need to solve the square root of minus 6 times I minus 8. And we again assume that the result will be another complex number, but we still write it in an ambiguous way, x plus y times I. And we need to find, of course, now this x and this y, exactly in the same way as we did in the previous part of this video. So we can rewrite this equation by squaring both sides of the equality sign. So we get minus 6i minus 8 is equal to the square of x plus y times I. And we know that this, of course, is equal to x squared minus y squared plus 2 times x times y times I. And this minus I squared is, of course, y squared I squared, but I squared is minus 1. And then again, equating the real parts with each other and the imaginary parts with each other, we get the following system of two equations. We get that minus 8 is equal to x squared minus y squared for the real parts. And we have that minus 6i is equal to 2xyi. And this will be the set of two equations that we need to solve in order to get x and y. We see that this y, of course, already cancels, and we find a relation between y and x as being y is equal to minus 3 over x. And this we will use later on when we found a value for x. And this value for x is found by looking at this equation. So we have minus 8 is equal to x squared minus y squared, but y is simply minus 3 over x. So we have minus 3 over x squared, which we can rewrite by multiplying both sides of the equality sign by x squared. We get the following equation. We get minus 8 times x squared is equal to x to the power of 4 minus 9. And we can rewrite this even further to get a nice fourth order equation. X to the power of 4 plus 8 times x squared minus 9 is equal to 0. And it is this equation that we will solve in order to find a value for x. And as before, we will solve this equation by doing the substitution u is equal to x squared. And why can we do this? Well, because we only have even powers of x. This means that we get the equation u squared plus 8 times u minus 9 is equal to 0. A very standard quadratic equation that we very easily know how to solve. We get that u plus minus, because we have two solutions, is equal to minus 8 plus minus the square root of 64, which is the square of 8, minus 4 times 1 times minus 9. We take the square root and we divide by 2. Doing the calculation, we get minus 8 plus minus the square root of 100 divided by 2, which is of course minus 8 plus minus 10 divided by 2, which gives us two solutions for u. We have u plus is equal to 1, and we have u minus equal to minus 9. Remembering that u was equal to x squared, we get two solutions for x squared. We have x squared being equal to 1 or equal to minus 9. And because x is a real number, x squared cannot be negative, so we can discard this solution. And this means that x squared is equal to 1, or x is equal to plus or minus 1. Remembering now that y was equal to minus 3 divided by x, which we got from this equation right here, we find our solutions for x and y. We have our first solution that if x is equal to plus 1, then y will have to be equal to minus 3. And our second solution, if x is equal to minus 1, then y will be equal to plus 3. And this means that the square root of minus 6 times I minus 8 is equal to either 1 minus 3i or is equal to minus 1 plus 3i. So we have two solutions for this square root right here. Now, of course, we need to remember why again did we need this square root? Well, let's take a look. We needed this square root because it appeared in the two solutions for our quadratic equation. We started with a quadratic equation. We simply used the method of solving quadratic equations, and in this solution we indeed got the square root of a complex number, which we first needed to take care of in order to proceed forward. But now we've taken care of this square root, so we can simply fill in this entire solution. So what do we get right now? We get, of course, that our z plus minus was equal to 1 plus I plus minus the square root of minus 6 times I minus 8 divided by 2. And now we know the solution for this square root, so we can rewrite this fraction as follows. We have 1 plus I plus minus 1 minus 3I. And we see that this plus minus here incorporates the fact that we indeed have two solutions. And we divide this, of course, by 2. And now we can simply calculate this to take this exercise home. For the plus solution, we have 1 plus I plus 1 minus 3I divided by 2. And this simply becomes 2 minus 2I divided by 2, which is of course equal to 1 minus I. And for the minus solution, we have 1 plus I minus 1 plus 3I divided by 2, which is equal to simply 4I divided by 2 or 2I. And we now have our two solutions right here, which are not trivial at all and are significantly different from each other. And this brings us to the end of this quite lengthy video. But I hope that you're now more familiar with how to take roots of complex numbers and how to solve quadratic equations which include complex numbers. If you have any questions, leave a comment in the comment section below. If you like this video, give it a thumbs up. And if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching and I will see you in the next one. Bye.